Alright, so let's get started now. We're good. Alright, see a few more people join. That's great. Alright, so we're just trying to go over OpenRocket. So again, this is our dashboard, our main menu. And we're going to start off with either one of three options here. A nose cone, a body tube, or a transition. I'm just going to choose a nose cone. And of course, the nose cone is what goes on top of the rocket. So we're going to double click that, and a pop-up window is going to show up right here. And we get options to play around with for the nose cone. So we can change the shape using these little scroll wheels. So we can either make it like exactly a triangle without any curve, or we can add some curve in by changing this variable to a 1 or anywhere in between. You can also change the nose shape. So right now we're on ogive, or however you pronounce that. We can go ellipsoid, and we get a more blunter tip for the nose. Really? Yeah, okay, let me change that real quick. Alright, there you go. So we can also change the nose cone length, make it longer or shorter depending on what you're trying to do. The base diameter, that's going to be the diameter of the rightmost part of the nose cone that is going to be touching the body tube. Yeah, I did. Wall thickness, you're not going to be able to see that on the display here, but the wall thickness is going to be the thickness of the nose cone. So if you're using one of the plastic ones we used this year, it isn't going to be, it's not going to be very thick. It's plastic, so we're talking, I guess, about 2 millimeters is about right here. So we can adjust that too. And we also have control over the material. Right now it's on cardboard. Usually we're going to use, we use polystyrene, I believe. Either that or, yeah, I think we use polystyrene. So I'm going to click that, and that's only going to change our, the mass of the nose cone. And that's going to be useful later. We'll talk about masses when we discuss TARC applications. And you get some more nuanced things, like you can change the paint finish. Tom thinks this makes a lot of a difference, but it doesn't really make that much of a difference. It's a little bit of drag extra if you choose like a rough finish. But if you want to be as detailed as possible, you might want to choose a smooth paint. Something like that would be how we make our TARC rockets. And we're not done with this nose cone yet. First now we need to go to the shoulder. And the shoulder is the part of the nose cone that goes into the body tube. And you'll see that right here when I increase the length and the diameter. So that's going to be inside of the body tube. And you're going to want to change this so that it is the inner diameter of the body tube. So that looks about good to me. You can change the thickness depending on what the nose cone you're modeling is. And that's pretty much it. Component mass, we can see that down here, 72 grams. That'll give you a good ballpark of what, how accurate the model is versus the nose cone itself. I'm going to hit close here. I actually think I double tapped nose cone when I first started, so I'm going to delete this. And deleting, you just have to go down here and press delete like that. And now I'm going to add a body tube. Notice how I clicked on the nose cone right here. That will be important. If I didn't do that, if I get out of that and I don't hit the nose cone, you don't have the rest of these options. You kind of need a parent object to add more parts onto. So again, if I hit the nose cone, you see the rest of the objects, the rest of the options pop up. If I go back to unclicking it, you're only left with these 3 base options. So I'm going to hit nose cone. I'm going to hit body tube, and we're going to add a body tube. A cool feature of OpenRocket is that it automatically adjusts the body tube diameter to fit that of the nose cone. So, that makes things a little more less of a grind to fix all the diameters of everything. So keep that in mind while you're doing this. We can adjust the length just like before, the diameter, stuff like that. Just going to have it like that, arbitrarily that long. We're going to change the material again. The type of material we use for our body tube is going to be paper. So changing that, you see the mass dropped a bit, and yeah, I think that component mass is a little too large here, so something might be up, but I'm not going to worry about it right now. It might be a little too thick. Let me go down to about 0.05. See that mass dropped about to where it's reasonable, about 50 grams. So keep an eye on that. The mass will give you a good guideline of whether you're getting the dimensions right and the material. Again, if we don't have anything on this little part tree selected, we don't get the extra options. So I'm going to click on the body tube, and then we're going to add some fins. And we have a few fin options here. We have 4 options. We're only going to worry about one of them, which is going to be the freeform fin. So with this, you're given a basic fin, and if you go up to this tab, the shape tab, you can change the shape of the fin just by dragging around these points. You can also change the coordinate of that point by going to this little interface here. So I can make this be at 2 centimeters, so 2 centimeters from the base of the fin, from the leading edge of the fin, and we can change this to be at a 5 here. So raising that up to a 5, and this makes it a lot easier to deal with than just dragging it around, a lot more precise. Typically, we want a fin shape like this, something like this. You can, of course, have it like this or anything you want. Oh, another good point. When you click in the middle of a line, it adds on another point, and the way to get rid of it is by control click. So right there, control click, and it gets a little messy if you keep messing around and dragging them, and you get a lot of points to deal with. So if you only want a quadrilateral shaped fin, you can just control click, get rid of the rest of the points, and only deal with these here. So we're going to go with that. General number of fins, we can change the number of fins we have. We can go up to, I don't know, maybe like 12, I think is the limit. We're going to have 4 fins for this. Don't really worry about the rest of these 2 options. We can also change the position of the fin here. So based on either the bottom of the parent component, which the parent of this, the fin, is going to be the body tube, because that's what we clicked on when we selected the freeform fin shape over here. So we can also have it be the middle, and the 0 point would be in the middle of the body tube or the top. And all these options just makes it easier to get dimensions from your rocket in the long run. We can also change the components, the component material here. We use balsa. It should be right about the top. And yeah, that's pretty much it. We can also change the cross section, but we won't worry about that right now. Alright, so we need to add a few more things in. Let's add in a motor tube, which we're going to use an inner tube for. So hit inner tube. Again, I'm going to change this to paper, and we're going to keep the defaults for now, just so we can get through this a little faster. And then the next tab over is going to be the motor tab, and you want to select this component is a motor mount. That will tell the program that you want to be able to put motors into this tube. And then we won't worry about this stuff right now, and we're going to close out of there. But there are a few things we're missing here, which are going to be the centering rings. So I'm going to hit the body tube again, and I'm going to add in a centering ring, which is another default we have right there. And again, you see it pretty much auto applies settings that it knows from the inner diameter of the body tube and the outer diameter of the motor mount, which is this little body tube right here. Alright, so we don't have to worry about that. I'm going to keep all the defaults again, and we're going to need to add in another one. So again, click on the body tube, click on the centering ring, and this time I'm going to adjust the position. So I'm going to drag it to wherever I think is about right. That looks fine to me. Hit close, and you know what? Let's give this a try. Let's give this a try. This looks pretty okay to me. So now in this main dashboard, we want to go to the top. See the rocket design. We want to go to the right one, motors and configuration. All right, so we're taking to this new tab. We want to hit new configuration. Down here, select motor, and then another pop-up tab came up, and these are the motors that we have available to us. If you really wanted to, you can import other motors. Like if it isn't showing up on this list, you can import them. That is a separate tutorial, I suppose. And you can go all the way up to O motors, which are, yeah, pretty big. So we're going to delete that. Remove motor if you want to delete the motor. Goes away. Select motor again. We're going to go to a smaller motor. I think we're going to use let's use a B4 motor, and we use that one. See, it's about the same size as the inner tube, which is what we want. That's why I selected that motor. It's going to fit the tube. Other ones might be a little too big, a little too small. That's a pretty standard size. So right now we have our engine, we have our rocket design. How are we going to be able to fly this? And let's show you how to fly this. We want to go to the top here, right next to motor configuration, flight simulations, and we want to say new simulation. And another pop-up tab came up. This will give you all of your options for setting the weather, the angle of the launch, like longitude, latitude, stuff like that. Little things that may affect the rocket, like the wind certainly will. If we max it out at 10, that'll give us a lot of trouble. So we can simulate with wind speed, we can do temperature, do a lot of different things. I'm not going to worry about that. I'm going to hit simulate and plot, and we get another pop-up, and this is just going to be giving us control over the graphs that show up once I hit plot. So right now we're going to have altitude, vertical velocity, and vertical acceleration. Those are kind of your basic distance, velocity, and acceleration graphs. So I'm going to hit plot, and here is our simulation. All right, and let's do a quick analysis of this really simple graph. So the red line, that's going to be our altitude. We'll look at that first. And again, all of this is going to be in meters. We can change the whatever unit you're using in the preferences. I think you have to go edit preferences and then use imperial units if you want to see it in feet. But for now, it's in meters. All right, so the red line is going to be our altitude, and we hit a maximum altitude of, what is that, 25 meters. So that's about 80 feet. Well, that's pretty good for a B motor of a rocket this big. And you can see we have a green vertical line signifying our apogee. That's our highest point in the flight. It gives you a good idea of, like, you don't have to, zoom in and see, where are we exactly, where are we the highest on the graph. We can just use this reference. We also have another reference here, motor burnout. That's when our motor runs out of fuel and the rocket itself starts to coast upwards. So, if we're looking at the vertical acceleration, you can see that we're accelerating a lot. We're accelerating until we hit this motor burnout. Then we're not accelerating anymore. We're not, besides gravity, we're not accelerating. Of course, we're accelerating downwards because of gravity, but we're not accelerating upwards because of the motor. And we can also see the vertical velocity, the blue line here. Our maximum velocity is around burnout, and then we go downwards from there, and we hit like the 0 mark around the apogee, which all makes sense. And from this we can kind of tell that we have a straight flight. We have no like weird graphs that are happening here. It's nice and smooth, and with time you'll be able to get a feel for what your graphs are supposed to look like and what problems may be displayed as. But for now, this looks pretty good, and we did a good job with our first rocket. So let me show you a poorly designed rocket so we can kind of learn how to fix it. So I'm going to go to the fin tab again, and let's say if I made these fins kind of a little bit small, like that. Let's see how that will affect the rocket flight. So I'm going to go to flight simulations again, new simulation. We get that tab again with the weather stuff, not going to worry about that. Another tab here with the graphs, going to hit plot, and now we get a different graph here. And with this graph, we're only hitting about, see, I zoomed in. If you want to zoom into a very specific spot on the graph, you kind of create a box by left clicking, and it will zoom in to that area, but that's not very common to do. So this is our graph here. We get a little bit wonky here. We're only hitting 18 meters, and that is because our stability margin is really off. And over here you can see your stability margin stuff. And I think most of you know what a stability margin is, but for those who may need a refresher, your stability margin is basically how well your rocket is going to respond to wind, or to being in an atmosphere, really. If you have a stability margin in the negative, like we have here, negative 3.008, that isn't going to be very good. That isn't going to help us out a lot. The fins aren't big enough to, stabilize the rocket. You really want a stability margin around 1.5, 1.7, somewhere around there. And we're not getting that here. We'll talk more about stability margin maybe when the school year starts, because we have a few physical models that we can show you to get a better feel of it. It's a little abstract. Don't worry about it right now. Just know that you want this number in the middle right of the screen to be around 1.7, 1.5, somewhere around there. And know that you can adjust it by manipulating your center of gravity, which is your CG, this blue dot right here, and your center of pressure, which is your CP, the red dot right there. You can adjust the center of pressure with your fins, and your center of gravity with where you distribute the mass of the rocket. So, the center of gravity is basically the balance point of the rocket. If you were to balance it on your finger, this blue point is where it would balance. Center of pressure is a little more abstract. We'll talk about that in the coming weeks, I suppose. Alright, so I'm going to fix this rocket again, and we're going to do that by moving the center of pressure this way, so to the bottom of the rocket or to the right of the screen. So I'm going to drag these out, and you see how fast that center of pressure goes over to the right here. Now we have a stability margin of 1.3. That's almost where we want it, so I'm going to bring this one out, and we see we're around 1.8. I'm going to make the fin a little bit smaller, and that's about good. And the reason we want this fin shape, this trapezoidal fin shape, is to prevent damage. So imagine that the rocket is coming down motor end first. If we had a fin shape like this, we might break off this very tip of the fin, and that's a hassle. We have to fix that. We maybe have to make a new booster section. We don't want to do that. So to give our rockets a little more durability, we can cut off that to begin with, cut off that overhanging segment to begin with, and now we don't have to worry about it, and we can get a more durable rocket that can be flown more times than a fin shape like this. Alright, so getting this back down to 1.6, that sounds good to me. And let's do another simulation. And simulate and plot. Alright, so now we're going back to our around 25 meter altitude, and that's another good flight. So that's how you can adjust the stability margin of the rocket. You can also do it another way by adding in a mass component right down here. And again, I can't click that right now because I don't have a parent object selected. So I'm going to hit body tube, mass component. And this is basically just, dead weight, ballast, maybe even a payload. Stuff that we put in our rocket to adjust the altitude for torque. We add in mass to get the rocket to go down in altitude. So I'm going to see how I'm increasing the mass of the object. Right now it's at 43 grams, and the center of mass went to the left. So if I increase it again, it'll go more and more to the left. If I decrease it to 0, that's where it was before. Let's have it at 10 grams. And again, like all things, I can adjust the position of this component. Let's say we put it in the very tip of the nose cone. And of course, the farther away you put the mass object from the center of gravity, the more of an effect it will have on moving the center of gravity. Alright, so right now we have a stability margin of 1.8 because I moved the center of mass. I'm not going to simulate it again just because it's not going to affect it that much. But right now we don't have a way to recover the rocket. The rocket right now is going to come up and, missile trajectory down. Usually we have a parachute. We'd like to be a little safe in this club, so we'll choose a parachute here. We can adjust the diameter, drag coefficient, don't really worry about that too much. Number of lines, so the lines coming from the parachute, the typical parachute shape, like down here, the number of lines will adjust the number of shroud lines. So we usually use 8 shroud lines in our rockets. So we're going to change that to 8. We can adjust the line length, the material of the shroud lines. We use Kevlar. I thought they would have it. I guess not. Keep it the way it is. That's fine for now. And of course you can adjust the position. We're going to say it's right about there. That seems good. We can adjust the dimensions of the parachute when it's packed. If you want to make it more dimensionally correct, it would probably be about that big. And we can have a deploy at. This is important. So the parachute will know to deploy at, right now we have first ejection charge of this stage. So when the ejection charge of the motor, I'm sure you all know what the ejection charge is at now, when the motor blows up going this way, that's when the parachute will know to deploy. And we'll see that on the graph. So that sounds good to me. Let's try simulating it, and I think we might have a bit of an issue, but we'll go over that. plot. And okay, so right now we have a time till, it lands of 5.75 seconds, and that doesn't sound right to me. If you think about it, wait. Yeah, so that sounds a little short, especially if we're going, around 60 feet. Might be ideal to get to a little longer of a flight time. So I'm going to increase the diameter of the parachute. Let's say 47 randomly. New simulation, again, simulated plot, and now we're hitting around 6.75 seconds. And right now we have another indicator, this vertical line here, saying we deploy our parachute at 3 seconds into the flight, or 15 meters. Alright, so that's how you do recovery stuff. Now I think that covers most of the basics of how to design stuff in OpenRocket. You have a lot of other options like couplers and streamers and shock cords, but a lot of that is, you can use basic knowledge of how to manipulate parameters with the basics over here with the more complicated stuff. So I think you can kind of explore that on your own, and learn about that. And if you have any questions, be sure to ask me about it. Alright, so besides that, we'll talk about how we use OpenRocket for TARC and what the next steps of using OpenRocket for you guys will be. So usually for TARC, we start off with our design parameters, our requirements that are handed down from us by the people running TARC. So we get a rule book, and we have to base our rocket design off of the requirements in the rule book. Right now, our requirements are that we have 2 eggs horizontally mounted within the rocket with 2 different body tube shapes, so 2 different diameters. And maybe we'll cover that in a minute in the design portion of, TARC. So we have a few things we need to accomplish. Typically, we start off with just getting a feel for what we're thinking of, so maybe we sketch out some rough designs on paper, talk about it with the team, get a feel for where everybody is, and then from there we go into OpenRocket and start to design that idea. So right now I'm just going to go through a basic rocket real quick that I'm thinking of doing, and from there, after that, we'll talk about what you should start to think about and maybe start to accomplish for TARC. Alright, so I'm going to say new design, new rocket. Here it is. New tab here. Again, I'm going to hit Nosecone, and base diameter 5 centimeters is a little too small, so let's say 9. And again, this is going to be arbitrary. I'm kind of rushing through this just to show you a few details that are more related to TARC. So in fact, I'm going to go back to this design. We'll work with this to save on some time. So let's say we want to add an egg, and you'll know that there isn't really an egg option here. So we're going to use a mass component, and this will be our de facto egg. Mass of an egg, it's around 55 grams, 55 to 60 grams, let's say 55. And we'll have it in this part of the rocket, and close out. We need 2 eggs, so again, I'm going to do that again real quick. Mass component. There's a, let me show you a shortcut so we can get some more experience with that. If I go to this, I believe that was the egg. Is there an option to copy? I think there is. Yeah, Control C, Control V, you can copy it, make another one without having to change the settings, and I'm going to just move that down right about there, right near the other egg, close out again. And now I'm going to change the inner tube, our motor mount. Right now, with this motor mount diameter, we can only use, A motors, B motors, C motors. Typically, for torque, we use F motors, so we're going to need a thicker inner tube to deal with that. So our inner diameter is going to be 2.4 centimeters. And it says no because our outer diameter is not right. So change our outer diameter first. Let's say 2.5. That sounds fine. And then 2.4 for the inner diameter. Okay, very good. All right, so you see this kind of got a little bit wider. So now I'm going to change the motor. So again, moving over to the motor tab. New configuration, select motor, and then I'm going to look for an F motor, any F motor, F32, that's what I want. Again, I'm just choosing that because we have experience with F32s and I know it'll be powerful enough to get us up to a decent apogee. And in fact, you can kind of get a preliminary feel for how the rocket is going to perform. Right down here in the bottom left, we have our apogee, maximum velocity, maximum acceleration right here, so we don't have to simulate it every time if we just want those few results. Alright, so we have our egg, we have our parachute motor, stability margin 1.35, that's pretty good. We might want to increase the mass of this little ballast up here to go to 24 grams. That's fine. Alright, right now I'm going to switch over to dealing with imperial so we can look at the 800 feet, trying to get to 800 feet without worrying about converting. So altitude, distance, feet. Alright, so hit apply. Is there apply? Next time you open a window, that's wonderful. Now I have to save Tark 1. Save as that. Open recent Tark 1. And then there you go, we get our feet. So you have to restart it pretty much to make any of the preferences take effect. Alright, so we're hitting 1100 feet here. That's a little high, a little higher than our 835 feet goal. So we need to add in another ballast weight to bring down the altitude. So hit body tube, go to mass component. We want the ballast that we adjust. This is going to be the ballast that we adjust. So we can add or subtract based on how the rocket is flying. We did this a lot during launches, so if we got over height during a practice launch, we would put in mass to this spot, or if we were under altitude, we would take away mass. So we're going to be dealing with this a lot, and we don't want this to affect our stability margin because that will add in additional variance which we're trying to eliminate. So we want to put the ballast that we're going to be dealing with. I'm going to call it ballast. You can name all the components of your rocket, so you're not left with unspecified. You can keep it a little more organized. So we don't want the mass we're going to be dealing with a lot to be anywhere but the center of gravity, so we can I'm adding a lot of weight, but the center of gravity isn't changing. If it was over here, if I add weight to it, it would change a lot. So that just gives you a little demonstration about that. So yeah, I'm going to keep that there. And you can see as I add in weight, that apogee goes down. So we want to be around 230 grams. Take that with a grain of salt. OpenRocket isn't the best with, simulating the apogee. And also we're leaving out a lot of components here that otherwise would take effect. So we're going to just assume that this is all right. All right, so we're around our target apogee. We have our recovery, we have our 2 eggs here, we have our ballast at the center of gravity. This is really rough. In fact, what requirement from torque are we kind of breaking here with this design? Does anybody know? Yes, we don't, and I'm not going to worry about that. You know what? Yeah, we are, just to show you how transitions work. I'm going to hit transition. I'm going to move it up. You know what? I'm going to have to delete the nose cone first because I'm going to have the transition up top. So transition, I'm going to move it. Oh, another good thing. If you have this tree of parts and you want to change, like if you want your transition to be on top of your body tube, you can drag it up there and you can make that be on the top of your rocket. Alright, so transition length, that's going to be of course the length of your transition. Very, very obscure, I know. The 4 diameter is a little trickier. That's going to be the diameter of the upper part of your transition. So increase it, it'll be larger, decrease it, thinner. Aft is the exact opposite. It's going to be the diameter of the lower section of the transition. We're going to keep it the way it is because it matches that body tube. Wall thickness, we covered that before. Transition shape, same idea with nose cone. We usually keep it conical. Shoulder, we talked about this for the nose cone. It's this part of the transition that goes into the body tube. So like that. You want to adjust it based on the body tubes you are using. And it usually has a auto calculated if I had an upper section here, but I don't yet, so we're going to keep it the way it is. Very good. That's our transition. Going to add in another body tube. This is going to be for the upper section. Again, we have this thing where it defaults to the bottom of the rocket. I'm going to drag it up to the top. And you see right there, it auto detected the transition and changed its diameter to be fitting the transition. All right, that looks good to me. Going to need a nose cone here. And keep an eye on the apogee while I do this. Right now we're at about 550. Let's see what happens when I add a nose cone. It shot up to pretty much our target, so that aerodynamic improvement really made an effect of around 300 feet, even if we're adding mass due to the nose cone. That's why aerodynamic forces are important to designing, and you want to consider them while you're doing it. But if you take a look, all of our stuff is going to be back here, and we're going to have an empty shell up top, and our stability margin is way too low. So I'm going to take the 2 eggs here, and I'm going to move them into the upper section. Just using this position relative to plus, whatever amount of centimeters. Alright, so that already improves our center of mass. Oh, that's the same egg. I'm going to move the other one up there too. Right there, that looks good. Running a good stability margin. But the ballast isn't in the right place, so I'm going to move it where it should be. And we see that we're running too high of a stability margin. So how should we get that stability margin to be lower? What should we do? Any ideas? We have 2 things we can manipulate here. Which one should we use? Yeah, fins. Let's do the fins. And we're going to want to make the fins smaller. Oh, see, right there I made another point on the fins, so control click. And if you ever forget that, it gives you a little reference down here. Click drag to add more points, control click to remove points. And then we're just going to make the, you see if I make it too small, the stability margin goes down too low, so I'm going to keep it around there. That seems good. Alright, that looks fine to me. Let's see how it flies. Oh, wow, would you look at that? Just by chance, we're 1 foot off our target. New simulation. That tab disappeared. Here we are. Simulate and plot. And you know what? That's not too bad. We're getting our apogee at just about our target for TARC, which is 835 feet this year. We are getting a duration of the from liftoff to touchdown of 39 seconds. That's a few seconds off from target. There's one problem here. Well, not much of a problem, but something to consider. Our parachute is being deployed a little early. Typically, we want the parachute to be deployed roughly speaking, a second after we hit apogee, so on its way down. Right now, it's deploying on its way up, which, it's not great because it's inconsistent. So we're going to be deploying our parachute while we're still going up. The parachute's going to be open. The parachute's going to slow us down as we go up. That's not going to be as repeatable as we want. So typically we want our recovery to happen after apogee, but it's not that big of a deal. We've had parachutes deploy during ascent, like around here. So not that big of a deal. Alright, the rest of the graph looks pretty good to me. We're getting a nice low descent. Yeah, so again, if you want to see like other events, so let's see if we want a new y-axis plot type. We can see, let's say, lateral distance, and see what that looks like. So our lateral distance is now in the yellow, or is that? No, our lateral distance is in green. So we're moving around when we're flying, especially if we have wind. We're going to be drifting a lot. So you can play around with that kind of stuff too. Get a lot of useful, maybe not so useful information. Okay, I think that's about all. And now we're going to kind of cover the next steps that you guys should be taking in this process, which will be starting to think of rocket designs as groups, maybe 3 to 4 people in a group, and start to discuss ideas, make some sketches on paper, and then afterwards go into working with OpenRocket and designing the rockets to be built. Hopefully we can get some rockets built over summer. That's the goal. And the first step along the way is making the design. We're going to have a few different designs this year, hopefully, just for some diversity. If one has a problem, the other ones, since they're not the same design, won't have that problem, and we can switch over. So yeah, that's why we're going to have multiple people making multiple designs this year. So, does anybody have any questions first off before we start talking about the logistics of that? Anything regarding OpenRocket? Yeah. For OpenRocket, like what I just did, or for like opening it? Okay. Yeah, I recorded this, so this is all I said was recorded, so I'll post that to the YouTube channel or something. Yeah. In fact, I'm going to stop recording for those of you watching right now. In the future, I hope you enjoyed, and yeah, let me know if you have any questions.